All right, so welcome to the third episode of the Questioner, the podcast where you can't get away with talking to a void. The idea is that I asked David here because he works on cohesive type theory, which I don't really know what it is, but I know it's like differential geometry and type theory, and I've been interested in it for a while. And he's gonna explain it to me, and I'm not gonna let him get away with anything that doesn't make sense. I'm gonna question him. I'm gonna grill him. I'm gonna put him on the rack, and he has had no preparation.
I've had absolutely no preparation.
Absolutely no preparation.
I haven't thought about this one little bit.
So we're just gonna see what happens.
Okay.
Yeah, and so we're gonna aim for maybe about 30 minutes. I mean, nobody watches these anyways, but I feel like a slightly smaller amount of nobody will watch them if they're like a reasonable length.
That's real. All right, could you let me share my
Oh,
notes
yes.
here just in case I need to write something down? I don't know.
Yes. Advanced. Can I say? Share screen, multiple advanced sharing options. All participants can share.
Okay, I will be right there. Let me get myself a piece of paper. And here we go. Okay. So we're going to talk about that's a lot of options. Cohesive homotopy type theory. And so
Okay.
to tell you about that, Owen, I'm going to tell it to you about it in reverse order. So first I'm going to have to tell you what type theory is. Then I'm going to have to tell you what the homotopy part of it is. But my big kind of like hill to die on is that there's nothing really fundamentally, crucially homotopical about homotopy type theory. It's just an enormous, amazing benefit that it is homotopical.
Okay.
And I'll try and make that clear. In other words, I'm not going to be using all this technology from algebraic topology, which is where the word homotopy comes from. Instead, I'm going to try and use really basic ideas and appeal to your intuition about mathematics already.
Oh, sweet. I like
it
that.
happens that this has a really nice interpretation that's sort of algebraic topological.
So
And then we'll
instead of
actually do
homotopy
that.
type theory, it's really accidentally homotopy type theory.
Yes, it's really type theory. In fact, it's quite true that in some sense, Martin Löf back in the 70s, I believe, wrote down the Martin Löf type theory, which is all these modern type theories are sort of based around, especially homotopy type theory. And Martin Löf had this type of identifications between objects, which I'll tell you about in a little bit. And he wanted to prove something about it, which he wanted to prove that these were like equalities, and so that you would only have one of them.
Yeah.
And he couldn't. And so he just threw in an axiom. He said, fuck it. And it turns out if you don't do that, you get like that he had stumbled on something really kind of interesting, which is that there actually is natively in this foundational math this higher structure of identifications that is equivalent to homotopy theory. So, and then the third thing will be cohesion, and these are the modalities of cohesion, and that actually brings the real homotopy theory, the real algebraic topology, into homotopy type theory, which doesn't actually have necessarily anything to do with homotopy theory. So I'm going to try to hit these beat by beat. So the type theory here, the idea is that every type of mathematical thing is a certain type of mathematical thing. So every mathematical thing is a certain type of mathematical thing.
Okay, I buy that. I buy that.
Yeah. Maybe I shouldn't. Maybe if this is like a listening thing, I shouldn't write so much.
No. This is going on YouTube. It's going on YouTube.
Okay.
Yeah.
So
you can see our beautiful voice,
mathematical
our beautiful
yes.
faces.
Oh, it's all here. Yeah, this is where the magic happens. So every mathematical thing is a certain type of mathematical thing. That's the basic idea of type theory.
Okay.
We have a shorthand for that. We say little a is a type big A to say A is a A.
Okay.
Well, little a is a big A. And so, for example, 3 is a natural number, and so we would write that like 3 is a natural number.
Okay. And why is this different from like just saying like 3 is an element of the set of natural numbers?
That's a great question. So in some sense, it's very similar. But in a very crucial sense, it's different. Because in set theory, being an element of the natural numbers is a proposition. It's a yes-no question. It could be true, it could be false. But for us, we're making the presupposition that every mathematical thing is a certain type of mathematical thing up front. It's part of what it means to be that thing. So when I say 3 is a number, I mean part of what it means to be 3 is that it is a natural number.
I see. It wouldn't make sense to say not 3 is a natural number.
Right, because 3, if I'm thinking really formally, and I don't want to get too formal, but if I'm thinking really formally, 3 is 0 plus 1 plus 1 plus 1. Like I count 3 times out from 0, and the only way that makes sense is if everything involved are natural numbers.
Okay.
Now there's also real numbers. We could have 3 the real number. Right, 3 is a real number as well.
Yeah.
You know? And the trick is that these are like different 3s, and that is actually something that is true in set theory as well. But people tend to pretend it isn't. But here's my proof that they're different 3s. In both of these have a multiplicative structure, the natural numbers and the real numbers, right?
Okay.
And 3 in the natural numbers, right, is not a unit. You can't divide by 3. But 3 in the real numbers is a unit. You can divide by 3.
Okay.
So they're different. They're different things.
Okay.
They behave differently.
Sure.
And how they behave depends on whether it's a natural number or a real number. So in other words, what we're really saying is that you got to know up front what you're dealing with.
Okay.
And so there's all sorts of things. It's not just elements of sets that are things, but like you could say that the natural numbers themselves, they're a set. Right?
Okay.
And we could say something like, R4 is a vector space over R.
Okay.
Right? So we get all sorts of mathematical structure there. We could say, we could say, for example, that, Z mod, 13 is a abelian group.
So is the natural numbers on the left side different from the natural numbers on the right side? When we say like 3 is a natural...
It kind of doesn't matter.
Okay.
You just take them to be the same thing.
Okay, fine.
So what I will say is that the natural numbers are just as sort of we have 3 the natural number, 3 the set. The natural numbers are a type of thing, right? And set is also a type of thing.
Okay.
And vector spaces is also a type of thing.
Okay.
And so what's the reason you can put them on the left as well as the right is because it's a type. Now a set is a special kind of type in type theory.
Okay.
And I doubt I'll have enough time to go through all the beautiful story of how homotopy type theory actually does that. But a set is a certain kind of type. It's a type. Well,
You can't resist. I gotta do
it. Because I'm going to tell you the next thing here. The next thing is that, okay, so we know that we have all these types of things. And then the next thing, that's our first one. Every type of thing is every math thing is a certain type of math thing. A type of math. I'm gonna put this back up at the top here.
All right.
This is principle 1.
All right. Ready? I'm gonna live tweet this from this YouTube video. Twitter. Every math thing is a certain type of math thing. David Jaz Myers. Every math thing is a certain type of math thing.
Good. So these are the principles of homotopy type theory. Every mathematical thing is a certain type of mathematical thing. I'm saying it in the wrong order.
Okay.
So
sweet.
And this is already how we think of it, you know, in most cases. Like, you don't say let X. You say let X be a topological space. You know?
Sure.
Let X be a real number. You already tell yourself what X is. You don't just say let X and then
right.
You know, that'd be crazy. So this is the first principle of
right. Only first
theory.
order logicians do that, and they're crazy.
They do, and it's weird, right?
It's weird. It doesn't make sense. Yeah.
You know, and it really doesn't make sense, and it makes you believe in a thing like a universe of all objects, and we know these kinds of like general like, you know, collections of everything to be sort of paradoxical, and it leads you down wrong roads. Yeah, of course you can fix it in all sorts of ways, but actually this is restricting your quantification is a perfectly good way to fix those problems. Oh, I should say, before going on, type of things is also a type of thing, and that's part of this power.
Uh-oh.
But this is just as contradictory. I'll put a big red thing. This is just as contradictory as the set of all sets. But the usual ways you fix that problem, like having Grothendieck universes or so and so, they all work in type theory too. So I'm just gonna.
All right, I'm not gonna let you get away with just pulling out something like, oh yeah, Grothendieck universes.
Okay, great. So there's a way in set theory that if you've heard of Russell's paradox, right? The barber who can't shaves everyone who doesn't shave himself.
Okay.
And if you run through that, he can't shave himself. Well, Russell's paradox is about the set of all sets which do not contain themselves. And there's a similar paradox you get if you have the set of all sets at all.
Okay.
So if all sets form a set, you get a paradox. And it's the same in type theory. And then there's a lot of technical ways to fix this in set theory, and there's a lot of technical ways in type theory, and they're all boring, and no one cares. And they're effectively the same way. So one of them in set theory is called Grothendieck universes, and that's the one we sort of ape in type theory. So if you know what those words mean, it's cool. If you don't, just think a type of mathematical thing is a type of mathematical thing. Like being a type of thing is a type of thing you can do.
It's like, as long as you just don't look too clear. Like naive set theory works. Like it's paradoxical, but like it works. It's fine.
It does. You almost have to try to hit the paradoxes.
Yeah.
If you're not trying to hit the paradoxes, you kind of can't hit the paradoxes. So. enough about those.
Okay. Yeah, we want to get to geometry.
We want to get to geometry. We want to get there. So, okay. So every mathematical thing is a certain type of mathematical thing. That's principle one.
Okay.
Principle two is for any two things. Of the same type, we can think of the ways all ways to identify one with another, with the other. So one thing I'll say here is that, so if we have X and Y, and they're both of type A, then we get a type, which is called the identity type, or identification type, or type of identifications. But we were really bold in homotopy type theory, and we just write it with the equal sign. And this thing is a type. Now, even though we write it with the equal sign, I wanna point out that this is not like saying that X and Y are equal. It's not the proposition that X and Y are equal. This is a whole type, and it's the type of every way to identify one thing with another. So, okay. I need to tell you about, like, identify.
So this is like, sort of a word. Is this like you have like two things and you line them up and you look at them and you're like, oh, they kind of line up, but then there are different ways of lining them up.
So a great thing here is if we have, let's say you have your own like, you know, picture here, this flat sheet, right? And so that's like a two-dimensional vector space, and I have mine. I have my own coordinate system. If we're both looking at a table, we're both looking at the screen. In fact, the way you look to me, I don't, you know, the space is all messed up with the zoom thing, but the way you're looking to me is mirrored, right? So my coordinate system of this screen that I'm looking at you is a mirror of what you're looking at me here.
So they're the same, but we have to say how they're the same.
They're the same, right? But if I said raise your right hand, I would have to be no, stage right. You know, in other words, I have to actually tell you which right. Am I right or you're right? And then we can do an operation which translates between our two different but same ways of doing things. So another really good example of this is clocks. If we have in our I should say really time zones. Let's say we all using.
Oh God! Oh,
time.
this is a nightmare, man.
Yeah, I know it's a nightmare. This precise kind of.
Are you saying that
really
homotopy type theory can cause me to not miss my meetings?
You know, I won't say that because you know, anything can happen. But if you are the kind of person who gets really into dealing with time differences, you might be like anal retentive enough for homotopy type theory. So, you're in the East Coast, I think, right now, and I'm in California, so we're in a 3-hour difference. And so that's a time difference, right? But really, it's a time sameness because the difference between our two times, the 3 hours, is how I can identify one of my times with one of your times. I can add 3 to it and then, you know, wrap it around the clock, right? So there's multiple different ways to do that, right? Like if you were in, you know, the central time, it would be adding 2, I think. And
we're gonna get lots of YouTube comments like, "You guys don't know what Central Time is 1 hour off."
Actually, it's daylight savings right now. But yeah, so there are lots of different ways you can identify these two clock systems. In fact, in that particular case, it's for every number of hours you could possibly shift by. But they each of them express a sameness, and that's the fact that they express a sameness. It's a way I can identify my way of looking at times with the way you look at times.
Sure.
So that's why we use the equality symbol here. So I could say this is that, like, let's say we have so e.g., you know, if let's say we'll take, you know, V and W are, or so let's just say V and R, you know, 2. And they're both vector spaces over R, then we can have the type of ways of identifying this vector space with R2, right? Okay. That's a type. And we can prove that that is the type of 2-element bases of V. So how do I identify a plane, a vector space, with a plane with an origin, the vector space, with R2, my standard coordinatized plane? And the answer is that I give you a basis, right? I give a basis, and then the basis elements tell me what my coordinates are. It's a coordinate system. Maybe they're like this, or maybe they're like that. And so the identifying here is a way of doing things, right? It's a way of putting these two things together, and so in particular here it's an isomorphism. And there's multiple ways of doing this a priori. There's multiple different choices I could make, and each one is perfectly valid, right? So there's multiple different identifications I can make between these two objects.
So let's spice this up a bit for a second. Suppose we think of V and R2 as, instead of vector spaces, as affine spaces.
Yeah.
What does their type of identifications become in that case?
That's a great question. In that case, how do we identify it? Well, R2 is a really special affine space because it has its full coordinates. So not only does it have the 2 basis vectors, it also has that origin, right? So to identify an affine 2-dimensional space with R2, I have to give you an origin, and then I have to give you the 2 vectors that are linearly independent relative to that origin. So it's the type of origin elements, and then the type of bases of the vector space of differences from that origin.
Oh, so could it also be like triples of 3 points that are not collinear?
Yeah, that's a great way of putting it.
Okay,
that's
cool.
Awesome. Yeah. Yeah. And so you see that one of the fun things, you know, homotopy type theory gets this reputation of being really abstract, but a lot of these questions are answered really concretely. And for example, when you think about these identification spaces, it's a new thing. But like the answer, when you're doing really concrete things,
it's like, just 3 points that are not collinear.
3 points that aren't collinear. It's like geometry, and that's actually how we end up getting a lot of this cool geometry that gets to mix with this higher homotopy stuff, because the
Interesting.
homotopy stuff secretly comes into these identifications. The fact that there's more than one. So one thing I will say is that let's say we had two identifications, right? If we had two of these, so what if we had, A, which was an identification of V with R, and B, which was also an identification of V with R.
Okay, just with R now.
R2.
Oh, R2, R2, okay.
Sorry, my bad. So if we had two of these, and so, the way we identify them is choosing a basis, then we actually get a change of basis vector, a change of basis matrix.
Is this? Oh, and right, and we
something.
know from linear algebra that change of basis matrices are unique.
Yes, and so we're getting this. We're taking these two change of basis. The change of basis matrix is uniquely determined by these two things, and it's a matrix element. And matrices are like algebra. So the thing I want to say here is that what homotopy theory really is the study of the algebra of identification, and really the algebra that comes out of the ambiguity in how you can identify two things. And so that's principle 2 of homotopy type theory.
So linear algebra is hiding in the
linear algebra and all sorts of algebra. So if I did clocks, you'd get modular arithmetic hiding here, and you can get all sorts of things, all sorts of really crazy stuff hiding up in here. So let me see. So if I go back over here and look at top, we've done homotopy, we've done type theory here, and now we did a little bit of homotopy and homotopy type theory. Oh, I can tell you what it means for something to be a set. Real quick. Anyway, let's get on to cohesiveness. I don't know if that's the right timing.
Okay, yeah, why not?
We have types of things. For any two types of things, we have a type of all the ways to identify them. And this is always like, so for example, if you ever have mathematical objects that are built out of sets, the ways you identify them are you give an isomorphism. So
okay, sure.
The type of identifications between two groups is the isomorphisms. The type of identifications between two vector spaces is the isomorphisms. Between two topological spaces is the homeomorphisms. Between two manifolds is the diffeomorphisms.
How does it know?
How does it know? It's amazing. It's an amazing question. There's actually the best way to see that is that basically the way you build up all these types is out of very simple operations. You can form pairs, types of pairs that are in two types, and types of functions. And then you can calculate what identifications are for those. And every type basically, and then there's things like natural numbers, and you can also figure out what they are for those. It's just equality. And then from there, from just these basic building blocks, you build up all the other definitions. But because they were built up out of these building blocks, you can undo the building block definition. So an identification between pairs is a pair of identifications. An identification between functions is a function into identifications.
So you can't write down the definition of a vector space without automatically coming up with the right notion of vector space.
Yeah. I can show you how that works a little bit, right? A vector space, so vector space, I'm not going to do the whole thing because it would take forever, but vector space, right, is one, a set V, an operation plus V to V, V cross V to V, a 0 in V, and then, a scaling, which is like, from R cross V to V, and then all of and laws. And the laws are actually elements of types, right? Because they're identifications here.
Sure.
We would have something like, like associativity is of type A plus B plus C is in this type of identifications. B plus C.
Okay,
and
sure.
So you have all of these things. And so what you can see is that this is actually a large tuple of
Okay.
functions and identifications. So if you know how to compute identities for tuples, functions, and identifications, and you can do that not so bad, it's in the hot book if you're really interested, you can compute what identification for vector spaces is, and when you do it, you get isomorphism, and that's magical.
That's cool.
It always gives you the obvious ones. In fact, it's probably the right definition for obvious if you wanted to formalize it. Okay. Cool. So that's 1 and 2. 1 is every kind of mathematical thing. Every mathematical thing is a certain kind of mathematical thing, a certain type of mathematical thing. And any two things of the same type, we can think of all the ways we can identify them. And that depends on context, but in homotopy type theory, we compute what it means from their type, which is amazing. So, okay. And this is why it's sort of really powerful. Another thing I can say is that every function respects identifications. So you don't have to, if you're doing maps, if you define a function of vector spaces, it automatically gives you a map on isomorphisms between vector spaces. So you don't have to check like you would in traditional set-based math. You would have to, define the map on functions, then go and check that it actually did something for isomorphisms. In homotopy type theory, it's a crank, and a computer can turn that crank sometimes. Sometimes. Okay, I'll get to principle 3. So one is really the type theory. 2 is really the homotopy. It's secretly in there.
Okay, and 3 is the cohesiveness.
3 is the cohesiveness.
This is the one I'm excited for.
Okay, here we are.
I'm ready.
And 3 is gonna be. Let me collect my thoughts and think about how to phrase this.
Okay.
Let me give you a little setup before I do 3. So there's a fact, a really cool fact. So if you don't presume the law of excluded middle, which is like every subset has a disjoint complement. Every subset has a disjoint complement.
Okay, that's an interesting formulation of the law of excluded middle.
It is, but it's the one that makes it sort of sound the most odd, because it's not true for spaces. You see, every space doesn't necessarily have a disjoint. Every subspace of a space doesn't necessarily have a disjoint complement.
Right. That's the definition of connected. If a space is connected, then no non-empty subspace has a disjoint complement.
Exactly. So here, what the way I phrase this is to try and get you to think that the law of excluded middle is somehow saying like, no, we're not using spaces. And so if we don't do the law of excluded middle or the axiom of choice, and I'm just not going to go into the axiom of choice. I'm not going to go there.
A wise decision.
Right. But it's safe to say that there's a similar way to think of it as somehow getting rid of your continuity.
Okay.
The choices you make are almost never continuous. Then there are models of set/type theory where every function from the reals to the reals is continuous. So, in set theory, without the law of excluded middle and the axiom of choice, the proposition that there are discontinuous functions or that every function is continuous is actually undecided. There are models where it's false, of course. Not every function is continuous. That's what the one we're used to. That's why we sort of learn this as an extra thing. But there are models where it's true. And
Can you do better than that? Can you say that every function is smooth?
You can, but it depends on what you mean by the real numbers. So
okay.
I do like to do that, but as far as I know, no one's been able to figure out a definition of real numbers in fair type theory from nothing else, no assumptions, that when you do it in classical math, you get the regular reals, and it proves the proposition that every function is smooth. I think it might be possible. But so far, the older ones I know use a little bit extra juice somewhere.
Okay.
But by this real numbers, I mean the Dedekind cuts on the rational numbers.
Okay,
like the very
Dedekind cuts
traditional-
on the rationals. Okay.
You could use Cauchy sequences too. This is also true for that, but a little different than what I want to talk about. So these are Dedekind cuts on rational. So this is the like way you build up the real numbers in foundations. This is the real numbers. For the smoothness, you have to go away from the real numbers, and you can, but you can have something that works effectively like that. And I would love to talk about that. I'm definitely not going to have time to get to synthetic differential geometry.
Okay.
I'm going to do like Mike Schulman's real cohesion here.
Okay.
So this is just a fact. It's just a fact that if you don't assume the law of excluded middle, and you can't write down any discontinuous functions from the reals to the reals. And this is a fact that you kind of knew already, because if you remember, I'm assuming that if you're watching this, you took, say, high school calculus or something like that. If you remember, you could never, like, what did it mean learning that a function was continuous? I mean, the only examples of discontinuous functions you ever saw were functions that were defined by cases. And there's a reason for that. The only discontinuous functions you can define are functions defined by cases somewhere. And that's kind of wild.
Yeah.
But because of that gives us something really, really nice. So I didn't tell you how to define a function in type theory, but it's way easier than in set theory. So to define a function in type theory, so what this means is this: f of x, right? Let's say x squared plus 1. This is exactly how you define a function in type theory. You say x is a real number, except we use 3 equals to say definitionally equals, so defined equals.
Oh, 3 equals. Cute. I like it.
So if x is a real number, then this is a real number. And since that's the case, so we have f going from R to R, defined by x maps to x squared plus 1. That's how you define functions in type theory. You assume an element, and then assume a free variable, and then you write down something that's of your type, and that's a function. That's it. And so what this fact up here means is that since we have models of type theory where every real function is continuous, right? Having a free variable implies a liminal sort of continuity in that variable. And this is really true because, in fact, in type theory also, if you have say Rn to vect a function Rn to vector spaces over R, this is a vector bundle.
Vector bundle.
So this is a continuously varying family of vector spaces. If we use the other real numbers, it would be smooth as well.
So this function u, for every point in Rn, you get a vector space. And you're saying that the vector space that we get continuously varies?
Yeah, so there's a normal way to do that. The normal way is that you say you have this kind of thing here, sitting over here, and then you topologize both. This is the normal way. You topologize both, and you say that the inverse of image of any point is a vector space. But no more than that, you say over every open set, this is, over this, it becomes a trivial product of the vector space and the thing, and it's a definition.
Yeah, it's a whole thing. It's a whole thing. Okay.
Instead of doing that, in homotopy type theory, you just say, well, it's a function. A vector bundle, I have a vector.
It's a function. All functions are continuous. I want it. Yeah.
Exactly.
Okay.
So this is a wonderful world. So what this says is that all you have to do is not assume law of excluded middle, and all functions are continuous.
Sweet.
Right? And it's just kind of like how old Martin Love had to do was not assume that any two identifications are the same, and you get all of this richness of homotopy theory. You just stop, just woo way. You go with the flow, and you get like more structure than you really thought possible. But there's one hitch, which I think anyone who is listening could sort of obviously point to, which is that not every function's continuous, right?
Blasphemy.
I know, right? So every function's continuous, but not every function's continuous. So
Oh
what do we
no.
do? So in a free variable, so the idea here is in type theory, and this is true of set theory as well if you don't assume exclude middle, but I'll just work in type theory. In type theory, a free variable x of some type implies a liminal sort of continuity. No matter when you assume you have a free variable, everything that depends on that free variable is going to
What do you mean
depend
by
sort of
liminal?
continuously. I mean that you can add axioms to take it away, like the law of excluded middle. But if
Okay.
you don't, it's there. So it's sort of like not. There's sort of a meta not
It's
going on.
it's like you can't give a counterexample to its continuity.
You can't give a counterexample. That's right.
Okay.
Without axioms. And
so you can't without axioms you can't rip you can't rip X apart. You can't do cases. Okay.
Yes, exactly. You can't say one. How do you think about this? Well, one thing is that having a free variable is like saying for all, right?
Okay.
But one thing you can't do is you can't say for each, right? For each individual X, I'm going to handle them totally separately. That will let
you have to handle them all the same.
You don't handle them uniformly.
Okay.
Right? And so, but for that reason, we can add in another thing which says, okay, but sometimes we do want to handle them each, right? And so we add in another thing. So to get discontinuity, we add crisp variables. Oh, it's such a great word. And the crisp variables are denoted with a double thing.
Oh man, but then what do you use for list comprehension? Or for cons?
Nothing. You use cons. The whole thing.
You can't. No, you have to save. You have one of single equals and one of double equals has to be cons.
You'll see. Well, in Agda, they get around this by writing it with a square, like colon square brackets flat square brackets. And what I'm saying, actually, everything can be formalized in Agda. So
cool.
If you're an Agda person, you can do this. And what I'm saying is actually
Agda can have crisp variables.
Agda now has crisp variables.
Wait, is that is that something that you can is that something that has to be built in at like the Agda level? Okay.
At the base. Yeah, this is one of the tricks is that there are certain things you do in type theory that you can just throw axioms in, and then certain things you do that you have to change your entire type theory.
Oh, and this is the latter one?
This is one of these
It's
things.
a whole new type theory.
It's a whole new type theory because it has a whole new kind of variable.
Okay.
Which is a discontinuous variable or crisp variable.
Wow. Okay, this is wild. Okay, cool. Go on.
So, cool. So, the difference is this, is that, like, I could say this. So, if X is crisply a real number, right, then I can do a case analysis, and I could say, like, 1 if X is positive, and negative 1 if X is, well, hold on a second. Yeah, let's say negative, and then 0 if X is 0, right? And so that is going to be a real number. And I couldn't do that if X wasn't crisp, because what I don't have normally is the ability to do case analysis on regular variables, because I want them to be continuous.
So how do you know that you've covered all the cases? Like X greater than 0, X less than 0, X equals 0.
So it's gonna be come down to the normal way you'd prove that this was a union in regular set theory. So the hidden axiom here, and I'm trying not to say it because I didn't tell you what a proposition is. Okay. So the hidden axiom is that axiom, which is the law of excluded middle, is for any crisp proposition.
It's either true or false.
And P. Yeah, either P is true or false. So whenever you're dealing with crisp stuff, you can work in like the regular math.
So this is like a way of like sneakily like having your cake and eat it too. You have exactly. You have all this groovy, everything is continuous, but then when you want to do real math, you
when you wanna torture your variables.
yeah, when you want to torture your variables, exactly.
You can cut them up in all sorts of nasty ways.
Oh, brutal. Okay, cool.
Yeah. So I think oh my God, I don't know whose quote is, but someone says that that Cantor ground the continuum into dust. And so, which is such an amazing image, but that's what the law of excluded middle does. It lets us look at each number in the continuum.
Oh, they're no longer continuous.
Separate, so no longer a line, they're just dust. And it's useful to do that sometimes, as we've found over the course of the past 100 and so many years of mathematical research. But it's really nice to not do that, because if you separate out when you're going to do that with these crisp variables, you say no, this one is going to be discontinuous, right? Then everything else you do is automatically continuous, and you never have to check. And that includes not just functions, but bundles, and even higher bundles and stuff I'm not going to talk about.
So it's like
really painful to check continuity at a certain
in normal math, you have to add continuity as like a special thing. Here we add discontinuity as a special thing.
Exactly. And that's why I like to think of this as the Wu Wei approach to axiomatization, where what you do things by not doing them. You go with the flow, you let it do it as it is, and you just take things out, and that's how you axiomatize. And on that note, once we have these things, we can give a sort of a underlying set of discrete take things out. We can take all the continuity out of a type. So taking continuity out of a type, and that's we say x, and we send it to this thing called flat x, and this is x but no cohesion. So I should say that I'm using the word continuity, and Levier, who came up with axiomatic cohesion, which is sort of what it ends up being this Mike Schulman's cohesive type theory. Levier wanted to use continuity, but of course we have this very robust, good definition of continuous. It's formal, so he needed another word, so he chose cohesion. So the idea of cohesion is that if we don't ask for the law of excluded middle and other things, our types are naturally cohesive. Like the real numbers are like a line. You can't just like rip them apart without damaging them, without breaking them.
So here's a question.
Mm.
In homotopy type theory, like, my intuitive model of this is that you're identifying spaces up to homotopy. So, like, a point is contractible, but also a disk is contractible. So you can identify a point with a disk. But now you're saying that I can, like, somehow split it out into all of its points. And so, like, how does... So somehow this like does this flat operator respect identifications?
This is a great question, Owen, and I'm glad you asked it, because this is a misconception due to the fact that we talk about it as homotopy type theory, and so I really should have front-loaded this. But in fact, right, what is the disk? Let's talk about it. Here's the disk, right?
Okay.
And so this is the disk D2 or whatever. And it is the subset of our R2, and it's defined, right, to be all points x and y, such that x squared plus y squared is less than or equal to 1.
Yeah.
Right? So one thing I want you to know about this is that it's a set of pairs, right? And so identifications between this is given by identifications between each pair, element in the pair, right? And identifications in the real numbers are given by being equal. I didn't say that, but the real numbers, that's what it means to be a set.
So the real numbers are a set.
Being equal. The real numbers are a set.
But the real numbers are also a space. How does that work?
They are a space. So a set in the sense of homotopy type theory means that to identify two elements just means to show that they're equal.
Okay.
And the homotopiness comes from so what is a homotopy? A homotopy is a continuous deformation between things, right? The identifications are not homotopies. Right? So there's no way to identify this type with a point.
Okay, but
there would be a homotopy between them. So this is this tension you're feeling, this opposition, this contradiction, if I could say, of two things you're holding in your mind that appear contradictory. That's a productive contradiction. That contradiction is giving rise to this theory, which is here.
But say I have this disc, and I want it, like, okay, you say I can't identify it with the point, but I want to identify it with the point.
Great.
What do I do to it so that I can identify it with the point?
I will identify it with the point. So this thing has no cohesion. So this thing is discrete. Right? And so the natural numbers are discrete. The Booleans are discrete. Most inductive data types are discrete if you throw in discrete stuff to start with. Discrete stuff are like just bags of points. They're just big bags of points. Right?
Yeah.
And so there is some relationship between D2 and the single point. So the single point's also discrete, right? And so if I have the disk, right? And now let's say I have a bag of points over here. So this is D, and this is some bag of points X. Let's say flat X to emphasize that this is discrete, right? And now let's say I have a map here. Well, that map, every map is continuous, remember? So that map has to be continuous. So it can't rip up the disk.
Oh, even though... Wait, so the disk consists of points. But it's not discrete. The disk is a set, but it's not discrete.
It's a set, but it's not discrete.
What?
Yeah, so it has this...
So that's the secret. That's the secret sauce. Even though like 1 2 is not equal to like 2 3, you still can't rip them apart.
Right, exactly.
Oh, that's so weird.
This is how you get the relationship of homotopy, because homotopy is coming out with what precisely can't you rip apart and how can't you. So if you look at this, when we take our disk and we map it into this big bunch of points, we can't rip it apart. So all of it has to go to one point. So what we would say here is that we have the single point, and then what we have here is there's a way of mapping this into there, which is just collapse everything onto this one point.
Right.
And what we're saying is that there is for any one of these, there is a unique point that it totally collapses onto.
Okay.
And this is a universal property, and it's a universal property of this map.
So for every space, there's like a discrete... There's a discrete space. There's like if you take like the category, if you slice under that space, then there's an initial element in that slice category.
Yes, and that initial element is the homotopy type, which is a discrete type. So I'll put it here. We have X here, and we have flat X, and this is like, you could think of this as, discrete set of points.
Wait, how does... Oh, yeah. Okay, right.
So
flat X maps into X. Yeah, that makes sense, because...
Spatial set of points. Right? So, like the actual disk that you can't, like, rip apart. Sorry, I interrupted you saying this.
No, go on.
So flat X is actually the terminal map from a discrete type. So if you're mapping in from a discrete type, you land in just the discrete points, and so you go into flat X. And then there's another one, which we call the shape of X. This is esh.
Esh. I like it. It's Hungarian. That's how you pronounce S in Hungarian. Esh.
Esh. Yep. So it's the shape of X, and this is the initial map from X to a discrete type, and a discrete type is one that is the same thing as it's flat. So it's if Y equals flat Y, then Y is discrete.
Oh, so if this whole thing is like compressed.
Yeah. So we collapse it into its points. But what's really remarkable is that thing isn't necessarily a set.
Wait, what?
Not often a set.
Okay, give me an example.
I will. So let's look at the circle.
Okay.
So here's the circle. Here's what the set of points of the circle. I can't really draw it because there's like a bajillion points of the circle. I mean, more than that. There's infinitely many.
Okay.
But it's like all the points, but they're not held together anymore. They can just freely move around. They're ground into dust. And you can label all the points in there by these points, but it somehow misses all the je ne sais quoi that's holding them together.
Okay.
Right? But there's another thing here, which is I need to map out of this. So one thing I can say is that this thing, which is initial, right? It actually is going to, how do I want to, let me see if I can do this right.
Yeah, why is this not just, if you're mapping into a discrete set, if you're mapping into a discrete type, like why is this not just squished?
If you map into a discrete set, it gets squished.
Oh.
If you map into a higher type that's discrete,
oh wait,
it
so
actually doesn't
discrete
all get squished.
is not the same thing as being a set.
Yes. Discrete is not the same thing as being a set.
Wait, so what is discrete?
Set, I really should call space. But
so what does discrete mean then?
Discrete means, I've been saying this and I never said it. Discrete means, well, my handwriting's amazing. That Y is equal to flat Y. Y is
oh, so like, so like, discrete is like sort of meta-theoretical. Yeah. It's given by our flat structure.
So it is meta-theoretical, and it comes from the flat structure. Let me give you an example of a discrete type which is not a set.
Okay.
Consider the type of any of two-element sets.
The type of two-element sets. Okay.
So being a two-element set is a type of thing you can be. So there's a type of them. That's the way to think about it.
So it's like a pair. It's a pair of like a type and a proof that type has two elements in it. Yeah, very formally, it's a pair of a type and a proof that type has two elements. And that is the propositions as types I haven't gone into, but that's like a really actually useful technology when you're doing this stuff. Okay. But we can think of it just as two-element sets. And so an identification between two-element sets is going to be a one-to-one correspondence between them. If you have two-element sets, like my two fingers here, my two fingers here, there's actually always two ways to identify them. Okay. I can identify them like this, or I can identify them like this. There's, there and there. There's always two ways. So in particular, there's more than one way. So there's not a set of two-element sets. There is a groupoid of two-element sets. So you have a set of ways to relate these two things, to identify them. And why is this discrete?
Well, it's discrete. You prove it.
Okay, you prove it.
One way I could say it's discrete because it is a type of discrete types.
Oh, because it's like somehow combinatorial.
It's somehow combinatorial. So a two-element thing is discrete. There's just 2 points floating around. They're not like hooked together somehow. And then it's sort of a meta theorem that you can prove. A theorem you can prove. It's not a meta theorem. It's just a theorem. That if you have a type of discrete things, then that type is also discrete.
Okay.
And that's actually that's one of my theorems that sort of started me off doing all this stuff. Once I had that one, everything else was smooth sailing. So that's a near and dear to my heart. It's not hard to prove. It's actually very, very easy to prove once you get set up. It's one of the wonderful things. But so you can, because two-element sets are discrete, any two-element set is discrete. The type of all of them is also discrete. So let's say I put two-element sets here. Let's say I did this. Move it down here. And so what would a map from this to there be? Well, for any point on the circle, I'm going to give you a two-element set.
Okay.
So I could draw this. If I draw the circle here, over any point, I have two elements.
Oh, okay.
Right? but it's over every point. So one way this could look is like this and this, like any two elements, and they cast a shadow there. And there's also another way. I could loop them up like this.
Okay.
So over any 2 points, at any point, there's two elements.
But they switch.
And these ones, they switch, right? So what I want you to see here is that if you imagine smoothly going along these two elements, right? Then you can see that there's, in fact, that how do I get, if I start at my two elements, right? And I smooth, every function's continuous, so I'm continuously going into two elements. So if you take two elements, right, and you're going to go in a circle and start back when you were, you'll see that if you go back, there's exactly two ways to do it. You go back where you were, or you go back and you flip it.
Okay.
Okay, if you do it again, let's say, what if you flipped it twice, right?
You have to get back to where you started.
You get back and they're in the same order. So either, right, you go back and you keep them where they were, or you go back and they flip them.
Okay.
Those are precisely the two ways to identify a fixed two-element set with itself. Either you say it's the same, or you flip it.
Sure.
You rename everything. It's opposite. And so what that's telling you is that this function, that there are more than one function here. Even though the circle's connected, there's more than one function into this type of two-element sets. And in fact, what we call this thing is the homotopy circle, and it's sort of a single point, but it has a non-trivial identification to it. And this is the shape. Well, this is circle. This is flat circle. And then there's a unique map here. So for any here, there's a unique here.
Why?
And that homotopy circle is defined by this property that to map out of the homotopy circle is to take an element of your type and give a way of identifying it with itself. And this is where homotopy comes in. So this is really the homotopy type. If you do this to any manifold, you actually get its real homotopy type, like the normal one that people expect you to get. And so you can go on from here and do tons of stuff. But I think that's where I'll stop the rambling now.
Yeah, I think that's perfect. All right, that was like 50 minutes,
an hour.
but like if
You did
you
a good job.
well, yeah, I think it was good, and hopefully if we've kept any viewers to this point, good job, viewers, you made it. And
Yeah, let me start citing things. So we have Levere.
oh yeah, okay, sure.
You can keep talking. I'll just write this.
Yeah, I don't know. I don't know what to say. Yeah, good job, readers. Give us feedback. Tell us to be shorter. I don't know. I mean, I love getting YouTube comments. It's always fun.
Yeah, I bet. I mean, this is a fun thing you're doing, Owen. It's fun to have like off the cuff math conversations. Really,
Yeah.
Just, like, you know.
So Levere axiomatic cohesion. Of course, it starts with Levere. That man's everywhere.
Yes, Levere. Like I swear, if you just go backwards in any citation thing in category theory, you end up with Levere, or at the beginning of the thing is a comment saying we were inspired by a comment made by Levere at the beach. It's Brouwer's fixed point theorem. How do you spell Brouwer? U-W. Incohesive homotopy type theory. And if you want to learn, this is about cohesion. If you want to learn about homotopy type theory, you can check out the homotopy type theory book or the book by Egbert Reicha.
Oh, I didn't know Egbert had a book.
Yes, it's really good. Also, Martin Escardo has a full course in literate Agda that's entirely on the web, and you can follow along.
All right,
so
cool.
That's a really good note, especially if you're a coding kind of person. So, yeah, and it doesn't do cohesion, but it would definitely get you ready to do all the cohesion stuff. Yeah.
Okay.
Cool.
All right.
Thanks, Owen.
Well, we'll sign off.
Signing off.
I'll send you the link when I post it. All right,
Sweet,
bye.
sounds good.